In this video, I will go over the same example for Ampere's law, but I will make some changes to show you how why it is important to use the right hand rule when you choose the direction of integration and the direction for the positive current. So the changes that I made here are the following. Now I have a conventional current that flows into the page. So my current is pointing in the negative z direction. Because of that, I know that the magnetic field will be curling around that current, around that wire, in the negative v hat direction. I continue to use the cylindrical coordinate system, and this is the dl in the cylindrical coordinates. I have written down Ampere's law, and now I have I'm going to calculate using equations 1 and 2. I'm going to calculate the dot product between B and DL. Now take a look here. I have B curling in the negative phi hat direction, and I have DL curling around the current in the positive phi hat direction. So because this is true for every point along my path, which is the same as before, I'm keeping the same path with a radius s, and I am moving counterclockwise. Because B and DL will always point in opposite directions, I know that the dot product will need to be a negative number. So I have when I find the dot product again, phi hat dot s hat and phi hat dot z hat will give me 0. So the only really term that survives is minus b s d phi hat dot phi hat, and this gives me minus b times s d phi. Now this is the dot product. I need to use not yet. I need to decide on what is mu naught times the current enclosed first. So let's say mu naught times enclosed. Alright, now pay attention here. According to the direction of integration, which is counterclockwise, okay, this is my path, a positive current will have to flow out of the page. Okay, so using the right hand rule, a positive current will need to flow out of the page. Now pay attention. The current that I have in this case is flowing into the page. Because a positive current flows out of the page and my current flows into the page, the current enclosed is mu naught times minus I. Okay, the reason why I included the minus sign here is because my current is moving in the negative current direction. Now let's call this, so let's say this is equation 4, this is equation 5. Now I'm using Ampere's law and equations 4 and 5, and this gives me the integral from 0 to 2 pi minus b s d phi. I'm gonna do the integral first. It will give me minus b times s times 2 pi, and the right side of Ampere's law is mu naught times minus I. The minus signs go away, and I get, for the magnitude of the magnetic field, mu naught times I over 2 pi s, which is a positive number. Very important. I solved for the magnitude of the magnetic field. If you're finding the magnitude of any vector to be a negative number, then you know that you did something wrong somewhere. Okay, I solved for the magnitude of b and I found this expression, which is a positive number, and it has to be. Now, if I want to write the vector b, I need to use equation 1 for that, which will be minus mu naught times I over 2 pi s in the phi hat direction, with the minus sign will give you a b in the negative phi direction. So it is important, let's say if I was not careful about the right hand rule and the convention, then I would not have a minus sign here, and that means I would find a magnitude of b that was a negative number, which makes no sense. So be careful, make a choice for the path, the direction of integration. Make sure you are aware what's the direction of your positive current and use that when you apply Ampere's law.